And we have 3 labs with that. And I'll talk about that after we finish what I want to get to with the PowerPoint. But the lab we're going to do this week is picking a variable you want to mess with to see if that increases or decreases the rate of reaction. And so this one's mostly focusing on, do you know how to set up a lab? What data are you going to collect? You're going to have to do a graph, and we'll go through all that good stuff. And we really want to prep before we get here so we can just come in, collect the data, since we just have an hour versus an hour and a half. But I'll get to all those logistics towards the end of class. And then next week's lab is, we're going to get a little more quantitative, and we're going to learn about something called the rate law today. And we're going to use the colorimeters again. So that's kind of a nice one. You make your serial dilutions, you take your absorbance for each one, we make a calibration curve. And then, you know how before we'd stick like the Gatorade in there or the bullet solution. Instead, we're going to do a chemical change in the little cuvette and take a bunch of readings, or we'll need like a USB and we'll graph it. Sounds pretty nice. And then the last lab for this unit is a really fun one called Le Chatelier, and we're going to make the colors of the rainbow by adding a little of this or taking away a little of that, heating it, things like that, and messing with equilibrium. Then we'll go into acids and bases. That'll be 16, 17, test on that. Bunch of titration labs. And then 19, 20 is battery chemistry, electrochemistry. And then we'll be in review mode. So kind of exciting. Yeah, okay, and I'll talk about we got a couple outlines for tonight. Looks like someone's already on it. The chapter we're not doing is 18. It's a good chapter. It's about environmental chemistry, but it's not on the AP test, so I use that time instead for review. So, in case you're working ahead or anything like that. All right, let's go to our PowerPoint and get this started. Let's see. 14, here we go. Okay, so we're looking at chemical kinetics. So that word kinetics should sound kind of familiar from physics. So we're looking at speed and rates of reaction, which is, again, is a very lucrative part of chemistry to go into. Industry is always looking for how to make reactions go faster, or in some cases slower, like rust. That's a chemical change. We try to slow that down. That's a very big industry. Especially like in the Navy, they spend a lot of money on preventing rust. Or food going bad, that's a chemical change, and we try to slow that change down. Also, or we think now with the vaccine, how do we make the most vaccine per minute, right? Because that, or if you're working in a pharmaceutical company, the more of that pharmaceutical you make per time, better, right? Time is money. So, or like a medication, you might see XR or ER on a bottle, and that's slow, extended release, a little bit of medicine per hour or whatever. Maybe you want that, or maybe you broke your leg, you need immediate release right now, a whole bunch, fast, please. So there's a lot going into manipulating the rates of chemical changes. Okay, so again, with kinetics in chemistry, we're looking at, well, I guess in physics too, you're looking at rate, but for chemistry, we're looking at the rate at which your chemical change occurs, your single replacement, your double replacement, combustion, any of that kind of stuff. And we did talk a little bit about this last year, but I think this is right when things got a little crazy in the spring. But this piece is completely new, is called reaction mechanisms. So besides the information about how fast or slow reactions happening, think back to like Hess's law, you know how we like flip things, have spectator ions and cancel stuff. A reaction we see overall is like one step. There might be a bunch of mini steps behind it. Oh, kind of like the bullet lab. We had like some steps before that happened. So that'll be like the second half of the chapter, and that is called reaction mechanisms. Maybe there's some spectator ions we never saw, or maybe it's a multiple step process. So those are the two pieces to this chapter. So we'll start off conceptual, and this is going to be closely tied to your lab this week. What are the factors that can affect reaction rate? One of them is the physical state, so solid, liquid, gas of your reactant. So for a reaction to happen, it's all about contact, collisions, hits. The more hits, the higher statistical chance of there being a successful collision and therefore products. So we watched this little video, how to get a date to the dance. And the kids had to run into each other, but not just bump into each other, with the right amount of energy to knock the books out of their hands, and they got a date to the dance. So the physical state is you want the most surface area exposed, and then there's a higher chance of contact or collision, and then there'll be a faster rate, a higher chance of successful collision. So in the video clip, it was traveling in groups. Only the outside kids have a chance to get a date or have that collision, and the kids in the middle, not so much. So like gases, that's why they're very flammable, because we're thinking combustion reaction. There's a lot of surface area, a lot of contact exposure versus like a solid. Actually, was there anything else on this? I thought, oh yeah, and the more homogeneous. So a lot of times we do aqueous in the lab, right? Mixed in water, a very homogeneous solution. It makes the reaction go faster. So that's why we're always doing that versus just like a block of salt. We're typically dealing with aqueous for the sake of time. Concentration is another one. So in the video, that's where they had more kids in the school, more collisions. So here we have some steel wool. And it doesn't, if I just hold steel wool, it doesn't start combusting. I have to give it a little boost. That's the flame to get it to go, because there is some oxygen particles out here. That's the other reactant, but pretty low concentration of oxygen. And so we give it a little boost to get that going. In here, there's a much higher concentration of oxygen. This is like 100% pure oxygen. So there's a lot more hits or collisions, higher statistical chance of successful collisions. And that's as soon as they put the steel wool in here, it starts combusting because there's so many more reactants, so more collisions. Now, say, as the concentration of reactants go up, your ingredients, more ingredients, so does the likelihood, it's all about statistics, we're talking about billions and billions and billions, that they will collide. The more they collide, the higher chance of a successful collision. Another one is temperature. We've dealt with that. So if you heat it up, it's going to go faster. You want to think of heating up as kinetic, increasing the kinetic energy. They're moving faster. So if we were all in the classroom and I was like, all right, everyone start running around, there's going to be a higher chance of a collision. Or so in the video, they cut the passing periods in half. So they had to run to classes. So it increases the kinetic energy or makes them go faster, which is the temperature. So higher chance of a collision, higher chance of successful collision. And same with the opposite, right? That's why we use a refrigerator or a freezer. We really reduce that kinetic energy. They're moving a lot slower. So if you have your, I don't know, I guess your avocado here, and it's going to react with a little oxygen. We slow down, lower the kinetic energy. So there's not as many hits, and the product is like that brown stuff that I don't want to eat. So less hits, less products, and sometimes you don't want the products. So that would be like food going bad. And then a freezer, we're lowering it even further. And there is a limit, though, to temperature. If you get it too high, the reactants might fall apart and not even get a chance to react. Maybe they'll decompose and do a different chemical change. So there is like a sweet spot for speeding it up with the temperature. Oh, and this is why we get a fever, right? Our body's trying to get those reactions to go faster to help us out, fight whatever's attacking us. And that's how you know, like, oh, there must be some foreign body or something going on because your body's increasing temp to get these reactions to go faster. Now, a catalyst, that one is one that there's a lot of research going into for industry because, again, we're trying to get reactions to go faster. Time is money. So a catalyst, typically they're like expensive metals like platinum and gold, and they help the reaction go faster but without being consumed. And in the video clip, it was the matchmaker. So instead of colliding, and we'll learn what they do in this, but they find a different way for them to meet. Instead of people having to run into each other, they help them get together, and then they're not part of the relationship, they're out. And they can help another couple get together, or the other reactants to get together. I went to this webinar, and this guy that teaches at OSU, he has like a PhD in organic chemistry, and his like side passion is coffee. So he was doing a talk on all this chemistry on coffee, and it was really interesting. But he's like, that's not how I get my grant money, is not the stuff on chemistry. It's his stuff that he does through his NSF grants is looking for catalysts that aren't as expensive or not rare earth metals. And industry is very interested in that. So you don't always have a catalyst. For our lab, we don't have a catalyst. So you have to choose one of the other factors. And so that's one of the things you're going to decide, like, which factor do you want to mess with? How are you going to mess with it? What's your independent variable? What's your dependent variable? And you're going to have to make a graph. So what data are you going to collect? What are you going to graph? So you kind of know like what's going to speed up and slow down a reaction. So AP wants you more with this lab is do you know how to set up an experiment is what this one's kind of more focused on. The thing we're going to learn next when you're doing this lab, pretend like you've never learned it. We're learning something called rate law. But with this lab this week, you're just like picking a variable, messing with it, and learning, like making sure you know how to collect data correctly to make a graph, stuff like that. And I'll go more into the exact details of this lab. That's kind of big picture. Oh yeah, catalysts are not consumed during the course of the reaction, which is kind of nice. All right, then we're going to get a little more quantitative. And let's take a look. It's like with physics, you're looking at a rate with like how fast, time, but a distance. Can't really see how far the chemicals are going. So what are we measuring for the rate for chemical change? How do we know how fast or slow it's going? So let's take a look at this chemical change. Over here, before it started, we just have A, and it's red. And then 20 seconds later, we have some A and some B. And 40 seconds later, those change. So the rate, what we're going to look at is we're going to monitor the change in concentration. You could technically do the reactant or the product over time. So remember, concentration is molarity. And then the SI unit for time is seconds. So we're looking at molarity per second. Now let's take a look at this, and we can use thumbs up, thumbs down. What's happening to the number or the concentration of the red or A as time goes on? Is there more A or less A, or does it not change? Yeah, there's less, right? It's being consumed. So we would look at, okay, every 20 seconds, what's the change in molarity of the red from here to here, from here to here? And it goes down. That makes sense, because where is it going? It doesn't disappear. It goes in to make B. So what's happening to B as time goes on? Yeah, we're making it, right? So B goes up in concentration, and that's our product. So any product should be going up for time, and your reactant, in this case it's A, should be going down over time. And you can look at either one. The only difference is we'd put a negative in front of the reactants, showing like, oh, that's going down. And then the product should just be positive because we're making that. All right, so let's get a little more detailed on this process. That's kind of what we're thinking about on a molecular level. The first part was like, okay, what do they have to do to react? We need successful collisions. These are some things we can manipulate to get that to happen. Okay. So here's a specific reaction instead of like A and B. Let's look at something real. We have butyl chloride. Total side note, don't even know this, remember, I don't know if you remember like meth, eth, prop, bute. Bute is the prefix for fluorocarbons. And there's your chloride. But here's this guy, butyl chloride. We add some water and we get a chemical change. Here are your reactants. Here are your products. So here's before it started, 50 seconds later, another 50 seconds, another 50 seconds, another 50 seconds. So every 50 seconds, they were able to measure the concentration of butyl chloride. As time went on, it's a reactant, so you could see the concentration went down, which makes sense. The other side should be going up. Kind of like, when we do orbital notation, we start with the electrons up, even though we technically could do down. It's a convention. That's what we do. We do it in terms of reactants, but technically you could do products. But we look at how fast the reactants are going down. So what they did, right, is your change in molarity. This might look a little familiar from your mechanics, right? Only this is doing molarity over time. So 50 seconds was down here for each one of these. And then what was the change in molarity from here to here? So this minus this over 50 is 1.9 times 10 negative 4 molarity per second. And they go to the next one. This minus this divided by 50 seconds. You get this rate. Notice the rate isn't the same. It's not constant. It's 1.9 times 10 negative 4, then 1.7. And the rate goes down. The reaction goes a little slower as time goes on. Think on a molecular level, and then rates measured in molarity per second. Any thoughts or ideas on why the rate would slow down over time? Any thoughts? You're thinking on a molecular, think about what's happening over time.
Miss P.
Oh, hold on, sorry, not you.
Oh, come on.
So what about concentration? What's going down over time? Reactants or products? Yeah, Mariella?
The reactants.
The reactants. When we said concentration makes it go faster, right? When you add more, over time, you have less reactants because they're becoming products. So there's less reactants, so less collisions. So it slows down a little bit towards the end. Or I shouldn't say end. I mean, I guess end. Eventually, there's nothing left. But it gets slower and slower because you're essentially lowering the concentration over time. And that's what it's saying. Hey, notice that the average rate decreases as the reaction proceeds. And that's because there are fewer collisions between the reactants because there's fewer reactants. And so that's going to be important when we're looking at, well, when do we say the overall rate is? That's going to come in here in a second. We're going to look at a nice graph here next. So we have concentration over here. Now we're just like graphing it. Time down here on the X. And it's not exactly a nice R squared close to 1. Close-ish, right? There's a little curve here. That's because, remember, it slows down as time goes on because there's less reactants. Same reaction here. So we plot this reactant over time, and you get a nice curve like that. Any line tangent to the curve is your instantaneous rate. That might sound a little familiar. Again, it's a little different. So the best time to take a rate, like when we were saying, like, this chemical change has a rate of blah, blah, blah. We take the rate towards the beginning. And we say that's it. Because as long as you keep adding reactants, then you'll get like a more constant rate. So we say somewhere up here, and you can see your rise over run here, right? All reactions slow down over time because you're losing reactants, lowering concentration. So the best indicator of the actual rate of a chemical change is near the beginning of the reaction. So that's an important concept, especially in lab and industry, things like that. The next thing we're going to look at, and there's a sample problem in your book, is how do you compare the rate of this disappearing to this disappearing, or this disappearing to this appearing? And for that, we're going to look at the mole ratio. So this reaction, it's all balanced, which is nice. It's a 1-to-1-to-1 ratio. So remember, rate is your concentration over time. They're going to be relative to each other. They're going to be the same. This is going to disappear at the same rate these are going to appear because it's a 1-to-1-to-1 ratio. Notice this little negative. We do that for reactants just to show that that's disappearing or being consumed. And the other side's positive because that's just a convention showing that's being produced. Kind of like with like calorimetry or thermo, right? The negative just means the heat's released. So same kind of idea. But as we sadly know, reactions are rarely all 1-to-1-to-1. So what if it's not? We have a nice little template for that. So say we have this decomposition reaction of hydrogen iodide gas. It's like, well, how do they compare? We're going to look at the mole ratio. In this case, the reactants are going to have half the rate of change as each product. And again, no, so negative just means that's being consumed, the side's being made. And we have a little template for that on the next page. In general, the lowercase, that's going to be your mole ratio. It's 1 over your mole ratio is going to give you the relationship of this to this, or this to this, or this to this. And reactants are negative to show they're being consumed, products positive to show they're being made or produced. Any questions on that? And there'll be a good little, and they call that the, this is going to be different than the rate law. This is the rate expression, and we're comparing and contrasting within the equation itself. And we use the mole ratio. Just like when we're doing anything else, it's 1 of this to 2 of these. So this is going to be this product, I'm sorry, this reactant is going to be consumed at half the rate of H2 being made or I2 being made. Then we're going to roll into our last topic, which is going to be what our worksheet's going to be on. So that's like kind of one thing, pause. So we kind of went through the different factors you can manipulate. Next thing, how do you quantify rate? And we're looking at molarity per second of either the reactants going down or the products going up. And we can compare within a chemical change using the mole ratio. Now, we can also get an idea of how rate changes. Some reactants don't even affect the rate if you mess with the concentration, because maybe it's a spectator ion we don't know about. So that's the next thing we're going to look at, is called the rate law. So one can gain information about the rate of a reaction by seeing how the rate changes with changes in concentration. So we're going to mess with each reactant, try to isolate the variable and see what happens. So here's a bunch of data, and the only way to do the rate law, this has nothing to do with the mole ratio. So that's going to be an important distinction. I feel like the AP test, we usually throw like a multiple choice question on there. The only way to figure out the rate law is through experimental data. So they give you a set like this, and this is what is on our worksheet, a bunch of experimental data. So they did 6 experiments, and here's our reaction right here, our chemical change. Here's our one reactant. Here's our other reactant. And for the first experiment, they did 0.01 molar of NH4 and 0.2 molar of NO2, and they found the rate of the reaction to be 5.4 times 10 to the negative 7. Then in the next one, they doubled the NH4, and they kept the NO2 the same. So really looked at, okay, does NH4 mess with the rate? Yeah, it does. They said, okay, if we look at experiment 1 and 2, we can see when we double NH4, it doubles the rate. Let's look at the other one as well. So if we wanted to look at how NO2 affects the rate, we would pick 2 trials where this changes, but this doesn't change, right? Isolating our variable. So if we look, there's sometimes a couple of answers. You could do 2 and 4. Oh, nope, never mind, this changed. Those wouldn't be good. We could do 5 and 6. This stays the same, but the NO2, we double it, and it does have an effect as well. And it looks like that doubles. So that's what's saying, like, hey, also, if we look at 5 and 6, we can see if we double NO2, it also doubles the rate. Notice they say initial rate. That's just because when we looked at before, it always slows down over time. So it's more like semantics that we know, like, okay, it's in the normal range where we're looking at for rate. Now we're going to put this all together in something called the rate law. And the rate law always has this kind of setup. Rate with no numbers in it. When they ask for the rate law, there's no numbers in it. The rate is equal to little k, and if that's a constant, and you just write k in there. And then we're going to figure out how, but any of the reactants in brackets that have an effect, and they're raised to some number. And we're going to learn how to get that number. And that has, it's called its order. And that's, the order tells you how much of an effect that reactant has on the rate. or the other reactant has on the rate. And maybe it has no effect. So it literally won't even be in the equation. It would be to the 0 order. So we're going to learn how to set up our rate law, and we're going to use this as an example. And you have to have data to figure that out. You can't tell from just the formula. So what we found out in experiment 1 and 2 is the rate is directly proportional to the concentration of NH4. If this doubled, this doubled. Cool. We also found out in 5 and 6, if we doubled this doubled. So it's also proportional to NO2. So therefore, our rate is proportional to these two multiplied by each other, those concentrations. And this is the rate law for that reaction. These both have to be first order, and I'll show you how we figure that out. But this is the rate law. Rate is equal to some constant that's temperature dependent. It's also dependent on what your reaction is. We just put in K if it's asking for rate law, not any numbers. And it's directly proportional to these two. Let me see if there's something else I want to show you. Oh yeah, okay. This equation is called the rate law, and K is our little rate constant, and it's different for each reaction. Now, how we get these little exponents called the order. Let's go back to our data. So when we looked at experiment 1 and 2, and there's a sample problem or two in your book. I think this might be 14.3 though. Divide your bigger number by your smaller number. So 0.02 divided by 0.01. All right, that's equal to 2. Same here. Your 10 point bigger number, that's supposed to be an x, times 10 to the negative 7, divided by your small number, 5.4, times 10 to the negative 7. 10 to the negative 7 cancels. 10.8 divided by 10.4 is also 2. So 2 to the what equals 2? 2 to the first. So this is first order. So when we did our rate equals K times NH4, and you could write the 1 or not, but if it was a 2, you would write the 2, is first order. And we found that out by dividing our bigger by the smaller, set those equal to each other, and to what exponent does it give you that one? So let's look at the other one. Same thing because it was doubled, but if we look at 5 and 6, 0.0808 divided by 0.404 is equal to 2. So 2 raised to what equals 4.3 divided by 21.6. 10 to the 7 cancel. These are divided. 43.3 divided by 21.6 also equals 2. So 2 to the 1 equals 2. So the NO2 is also first order. So you divide the bigger one by the smaller one, the concentration and the rate, set them equal, and then figure out what this power is. And that's your exponent, or it's called the order. And then the other important thing is you want to pick trials where whichever concentration you're looking at, that's the only thing that's changing. And we'll do another example problem before we talk about the lab. Any questions so far? Okay. A couple more little vocab, I think. So the rate law shows the relationship between which reactants affect the rate law and how. That's the order. Maybe it's to the second order, a third, or a first, or maybe it's 0 order. Both of these happen to be first order. So the exponents tell you the order of the reaction with respect to each reactant. A lot of R words there. Like alliteration. This rate law we found out was equal to this. This is the rate law, no numbers. This is the constant. This is first order, and this is first order. And then you could also have an overall order. So the individual orders are these exponents here. And that tells you the specific relationship. The rate is dependent on each reactant. And then another question could be, what's the overall reaction order? You just add up the exponents. So this one is based off of 2 first orders. And so it's second order overall for this particular reaction. All right, let's walk through an example. On your homework, there'll be 4 problems just like this example. And again, this 1 and 1 had nothing to do with the fact that this was a 1-to-1 ratio. You can't just look at this reaction and write the law. You have to have some experimental data because you don't know if there's a mechanism behind it or like multiple steps that got canceled out. All right, so let's take a look at another one. It was just coincidental that it didn't have to be first order. All right. All right, here we go. So this is how your homework is going to look like. Determine the order of each reactant. Write the rate law. We're going to solve for K, but you need the rate law first. So first, let's find the rate law. Then we'll find K, and I'll show you how to do that. We just do some substitution. And then tell me what's the order of each reactant and what's your overall order. And that's what we have. We have just 4 questions like that on the homework. Okay, so here we have 3 reactants. So we know our rate law is going to be in the form of rate equals K, and then let's see how each of these affect the reaction rate, how fast it goes. What 2 trials or experiments do we want to look at to study BrO3? Anybody? Any thoughts on which 2 experiments we want to look at to study this guy, the BrO3? Yeah, Mariella?
I think 2 and 3.
That would be a good one for BR. Let's do that one for BR.
Oh.
So this 2 and 3 are great because these ones are the same, right? They didn't change the concentration of BrO3. We didn't change the concentration of H. We only changed the concentration of Br. So that's a good one to look at for just Br. So let's do 0.3 divided by 0.1. So that's 3. Actually, I'll just do this. So for this guy, we have 3 to the x equals 96 divided by 32. 10 to the 4th cancels, right? Top and bottom. All right, what's 96 divided by 32? Yeah, take down the 3. Yep, so that's equal to 3. So we're going to do 3 to the x equals 3. So this guy is first order. All right, what else could we look at? We have 2 other reactants we need to look at. Jonah?
For BrO3, could we do 1 and 2 trials?
Perfect. So let's look at BrO3. Sorry, I'm looking for my annotate. There we go. Okay, we're going to look at this one now. He's saying, let's look at 1 and 2. All right, BrO3 changed. Good. These ones did not. These ones did not. So that's a good one to look at. So we're going to do 0.4, the bigger divided by the smaller, divided by 0.1. So that gives us 4. 4. I like to use a different letter so they don't get confused, especially if you're on a hurry in the AP test, you know. So 4 to the y equals, then let's do 32 divided by 8. Was that 4 as well, I think? Okay, so wait, 8 times 2 is, yeah, okay. So this one also happens to be first order. All right, we've got one more. What are some good trials to look at for hydrogen? Let's pick a different color. Amelia, any thought? Oh, Jonathan, go for it.
1 and 4.
Yes, I think. Yeah, those work. 1. So BRO3 is the same from 1 to 4. And sometimes there's multiple trials and they'll get you the same answer. So if there was another one where all of them were the same, that's totally fine. Let's see. 0.1 and 0.1, those are still good to go. But this doubled. Perfect. So we'll take 0.2 divided by 0.1. That gives you 2. So 2 to the z equals 32 divided by 8. What's 32 divided by 8? Yep, thanks, Mila. 4. So 2 to the what gives you 4. This one's a second order. Woo, changed it up. So our rate law, so part A is what's your rate law, is going to be equal to BRO3. Don't forget the brackets. They need to be brackets because that represents concentration. And don't forget your symbol. First order. I did not leave myself enough room. Let's do it here. Rate equals K times BRO3 minus times BR minus. This is first order. Oops. This is first order. And then the hydrogen. Oh, wrong color. Oh well. We found is second order. And it doesn't matter the order. Sorry, the word order again. Doesn't matter I was trying to think of a different way to say it, but the order that you write these in, you could have had H squared up front. It doesn't matter because they're all multiplied, right? So it doesn't matter. As long as you have the correct exponent, that's fine, but it doesn't matter the order of the order. So this is the rate law. Notice there are no numbers in it. You do want the brackets. So that's the rate law. That'll get you some good points. So that's A. Question so far on that. Okay, now let's do C. The order of each reactant. This is first. This is first. This is second. And then what's our overall order then? You can just hold up with your hand. Yep. So 1 plus 1 plus 2. It's fourth order overall. I just add up our exponents. Okay, the other question is what's K? Well, we can solve for that. We now have the rate law. I'm going to clear this all out. We know that rate for this particular and then also, well, no, right, source. Rate equals K BRO3 BR H plus squared. That's the rate law for this reaction. Notice this 5 didn't come into play at all. This 6 didn't either. There's usually like a multiple choice question or something that has that as one of your options. You want to know that the rate law has nothing to do with the balancing. Even if you forgot to balance it, you'll still get the right answer. Okay, now let's solve for K. Now that we know the relationship, pick any trial, doesn't matter, and plug it in. I'm just going to do trial 1, but any of them will get you the correct answer. So I'm going to substitute in 0.1 here, 0.1 here, and 0.1 here. And then the rate, 8 times 10 to the negative 4, and solve for X. So take some time, crunch those numbers. Try to put in your molarity. The units are going to be really important for K. Get the number, but try to put in your molarity for each of these. So 8 is 10 to the negative 4. Molarity per second equals X times 0.1, 0.1, 0.1 squared. On the left, I did 0.1 squared times 0.1 times 0.1. So you should go 1 times 10 negative 4. What about our units, though? Molarity times molarity times molarity squared. What do we do to exponents when we're multiplying? We add them up, right, guys? Right, so the little 1 plus the 1 plus the 2. So this becomes molarity to the 4th. So you have 1 times 10 negative 4 molarity to the 4th times x, right? Divide both sides. 1 times 10 to the negative 4 molarity to the 4th. What you do to one side, you do the other. 1 times 10 to the negative 4 molarity to the 4th. This canceled. And x, right, the 10 to the 4th cancel. 8 divided by 1 is 8. But we need the units. You'll get it. This is a short answer on the AP test. It's a whole point for getting the correct units on your K because they're going to be different every time. So we're going to have seconds in the denominator, right? That doesn't cancel. But one of these molarities are going to cancel. There's a molarity on top, and now this is going to go to 3. And so you have molarity on the denominator to the 3rd. So 8 seconds on the denominator, molarity to the 3rd to the denominator. Or you could write seconds negative 1, molarity negative 3, meaning they're on the denominator. And that is your rate law constant for this reaction. Any questions? We have 4 practice problems asking the same thing on these. This will definitely be on the test. This will definitely be on the AP test and my test. It's a good time to check in before we practice. Yeah, Mariela.
What did you say the units were? I can't really read it.
Yeah, let's see. Oh, so do you see how I got this to the 4th over on this side?
Yeah.
Okay, so divide by the 4th, divide by the 4th. This was molarity to the 2nd on top, molarity to the 4th on the bottom. So one of the molarities cancels.
Okay.
So it's seconds on the bottom, that made it, and molarity to the 3rd, because that 4th got knocked down 1, if that makes, do you see like, because that molarity on top,
Yeah.
now and there. So it's 8 with seconds on the denominator and molarity to the 3rd on the denominator. So that's like a little like fraction.
Okay.
Or you could do seconds negative 1, molarity negative 3.
Okay.
Other questions? That was a good one. Okay, so then let's look at the homework and then let's look at the lab. Oh, sorry. Did you have a question?
Can you say one more time the seconds that's underneath the molarity to the
Yeah, because you had, what did we end up with? We were at 8 times 10 to the negative 4 molarity per second, right, from this guy, equals x, and we divided both sides by 1 times 10 to the negative 4 molarity to the 3rd, which was what we got over here, divide. And then there's a molarity on top. There's 3 on the bottom, so just 1 will, oh, sorry, this was to the 4th. This was to the 4th. 1 will cancel, and you're left with molarity to the 3rd. And so this is on the denominator, and this is on the denominator. So you get 8 seconds negative 1, molarity negative 3, or you could write it as 8, 1 over seconds, molarity 3.
Okay, got it. Thank you.
Yeah, no problem. I know it's really messy. Okay, so the homework, very, very similar. You have 4 problems, and it asks, tell me the rate law, figure out K with the right units, and then what's the order of each reactant, and what's the overall order. And so there's your reaction, here's all your data. And there's 2 in the front, 2 on the back. And then a couple outlines. The other thing that's coming up is our lab on Thursday. So you either sign up for the 1:30 session or the 2:30 session. During the 1:30 session, the AP Physics 2 class will be in here as well. There's only 6 kids, and they will be in the lecture area up front, very, very front. And then in this, if you sign up for the second one, they will not be in here. So just as a heads up for that, making decisions. And here is our rate law lab. So I put the pre-lab, you're going to bring it to lab to get it stamped, just like old times. And let's talk about what we're doing for this lab. So our central challenge is to investigate the speed of a chemical change between solid calcium carbonate, I'm going to grab it, which is what's in seashells and chalk, exoskeletons. So I have it in this like pebble form and lots of different sizes, but you also have a mortar pestle available to you. Keep that in mind. Your task is to investigate, that's one of the reactants, and hydrochloric acid, aqueous. You can also pick the molarity on that. When you mix them together, I'll tell you what the equation is here in a second. We have a chemical change, bonds are broken, bonds are made, blah, blah, blah. And then you're going to pick something to make it go faster or slower and collect some data. So a lot of historical buildings and monuments are made of limestone or marble, which is a mixture. And one of the things in that mixture is calcium carbonate. Since the Industrial Revolution, air pollutants, specifically oxides, calcium oxide, things like that, sulfur oxide, nitrous oxide, they get absorbed in the atmosphere, chemistry happens, and we'll talk about that in acid-base chapter. But the rain becomes a slightly more acidic. So when you get some acid rain on your marble statue, it'll start kind of doing a chemical change. I'll show you what that is. And some of the edges will get a little softer looking and disformed because it's breaking bonds on the calcium carbonate to make these products that we'll see here in a second. So the acid rain will react with the limestone, specifically the calcium carbonate, eroding it and causing some disfigurement and damage. All right, so our pre-lab is really good on kind of like helping us figure out what we want to do for this lab. List factors you think might affect the speed at which calcium carbonate will react with the acid. So that's perfect part one of your PowerPoint, right? What are some things you can mess with, just in general? Thoughts. Number two, oh yeah, and this will be available in different chunk sizes. There's also a mortar pestle you can use, ice bath, Bunsen burner, hot plate, tap water or DI water. Choice is yours. There'll be a stock hydrochloric, but you can make different concentrations. No lower than 3 molar, just goes too slow, hydrochloric. And the maximum per trial you can use is 1 gram of calcium carbonate. You want to be less than 1 gram. So, because you're going to write a rough draft procedure before you get started. And when you get started in doing stuff, you might tweak some things. So I want to make sure you have a game plan before you start collecting data. Okay, so let's look at what actually happened. Oh, almost did that. Okay, in the chemical reaction, it does produce a gas. That's going to be one of our products. What's a way of monitoring how many products are being made, or as the reaction moves forward? What's a way you can measure how much gas is being made? Discuss how increasing the surface area, that's number 3, it just doesn't show up. That's 1, 2, and 3. Third question, it's a pretty short pre-lab. How might the surface area of a solid influence the rate of a chemical change? Kind of a nice little pre-lab. But you also need to have like a practice procedure or rough draft procedure. You can email it to me ahead of time, or you could bring it to the lab, whatever you want to do. You can work with a partner or not. And when we do the partner, let's see if I can move my camera. Hold on. Okay, hold on. Let's do conference cam. Okay, we'll be like, oh, that just went. But you'll stay like across the table from each other. I'll just show you when you come in. Okay, that didn't work out. But either way, it's fine. Okay, the reaction that's actually going down is this guy right here. It's a 2-to-1 hydrochloric aqueous calcium carbonate solid, and you'll be given these, and you make calcium chloride aqueous liquid water, so that'll just be a clear liquid. You won't really be able to see anything there, but you also make some CO2 gas. Now that's something you can collect. One thing we have is, so you have Erlenmeyer flasks available. You have these syringes. Oh, here it is. that have graduation marks in milliliters. And there's like a little stopper, like a rubber stopper with one hole in it. You can do the reaction in here. You can do the reaction outside, then pour it in. You got to kind of decide that when you're starting a timer. Are you using the timer? And this is closed. That's open. If you create a gas, right, this should go back. You might want to prime it a little bit, like because of the friction, give it a little bit, but note where it starts. That like rubber thing is like a good, like where are you saying is the start or where it's measuring? Do you want to have this closed, put it in here, and then open it? Do you want to open this whole time? All these little things in your procedure you want to think about. We have regular thermometers. We have the temperature probes for the Lab Quest. We have a pressure sensor if you wanted to use that. Same kind of idea. You hook this in. It's got a lure lock closed, open, and it'll give you pressure. Maybe you want to, something about moles and pressures relationship. It doesn't have to be super quantitative or like calculations, but you have to think about what am I collecting? First of all, what am I going to change? What's my independent variable? And what's your dependent variable? Because that's what you're going to want to figure out what you want to graph, how you want to change it, and what data are you collecting? So hold on. To show how A affects B, I think we have a little, to what extent does A affect B? A is your independent, B is your dependent. Your teacher will guide you through a process of identifying variables that affect rate, yada, yada, yada. There's no catalyst, but you have access to all the other things. And you need to come up with a practice. You're going to have a graph. So what do you want to graph? How are you going to collect that data? What variable are you changing? And you'll need a hypothesis. If I change blah, 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 then blah, blah, blah will happen. Trying to think. So like I said, you have a pretty good idea, just even from sophomore year, on what affects reaction rate. What AP wants you to get from this is how to set up a lab. So what your problem is, what do we want to collect? But don't do anything, pretend like rate law never existed though. We're not doing anything with that. We're just kind of looking like we hadn't even read anything on the chapter. So it could be very crude kind of data. It doesn't have to be a very super formulaic, but what are you going to compare and contrast? What are you going to graph to prove, to back up that changing that variable made the reaction go faster or slower? Another key thing is the more data you get, the stronger your argument is, the stronger your conclusion. That doesn't mean if, say, you're going to do temperature, you do a control and like 6 other temperatures. Do a control and 1, maybe 2 other temperatures, but lots of trials of your control in that 1 or 2 other temperatures. Does that make sense? You could slow down a reaction. You could speed up a reaction. Either one is showing that it affects the rate. But you need to have a control. Yeah. Any questions on things coming up? Let's see here. So that's Thursday afternoon. I'll see you guys again before. Oh yeah, you guys. I forget I have AP on different days now. I will see you the day of, I think we have class on Thursday for any last minute questions. And you want to bring your pre-lab stamped. I always have office hours like normal. Except for those half days, I'll have a 12:30 office hour. That's a little different, And you'll want to come with some sort of idea of your practice procedure, since we'll have like an hour to collect the data. Yeah, Gabrielle.
Could you explain again what you were saying about like the measuring the gas with the syringe?
Yeah, so when you and you have to figure out what your start time is too. But when calcium carbonate and hydrochloric acid combined, you basically get a salt water, not NaCl, but calcium carbonate and water. And then you also get CO2. Since that is less dense, you should be able to collect how much is made. But then how are you going to do that with time? right? So that's something to think about. And there's different ways. There's not like one way to do this lab. There are so many different ways. And then also think about, do you want to do the reaction and start it closed and then open it at a certain time or keep it open at the same time? But also think about when your sample lab, be consistent with all your trials. And maybe you have a rough draft and I approve it and then you do it and you're like, let's tweak something. That's totally fine. And you don't need to get it like checked by me. But you need to have some sort of idea before you go in and checked off. If you're doing partners, it could be the same plan, but make sure you have 2 copies so they each get like a stamp for when you upload your lab, I guess, if that makes sense. Other questions, logistic or chemistry wise? So what's due next class is the worksheet and the 2 outlines. And then for lab, the pre-lab, which is pretty short, honestly, it won't take you guys that long, but the practice procedure or rough draft procedure. Rough draft procedure is better. Feel free to hit me up if you have any questions between now and then. And I think that's it.